Wilhelm Röntgen's discovery of X-rays in 1895 was a turning point in the history of physics. This was rapidly followed by Henri Becquerel's discovery of radioactive radiation, the discovery of radium by the Curies, and the quantum revolution in atomic physics. During this period, in their quest to understand the structure of the atom, scientists were bombarding all types of material with high-energy radiation, also called ionizing radiation, because it would tear an electron off an atom, leaving behind a charged atom, or ion. Scientists also searched for radioactive substances in the crust of Earth, in the ocean, and in the atmosphere. Radioactivity was found everywhere, in caves, in deep lakes, on high mountain tops. The most surprising discovery was that it was impossible to eliminate the influence of all radiation. No matter how thick the lead plates were that encased the detector, there was still a detectable signal. These rays were more energetic than any type of radiation previously observed and could penetrate lead plates a meter thick. Hess set out to discover the origin of this mysterious, energetic, natural radioactivity. He made significant improvements in the sensitivity and precision of his detectors, and then personally took the equipment aloft in a balloon. During 1911 and 1912, Hess systematically measured the radiation at altitudes above 17,000 feet. The daring flights were made both by day and during the night. He found that there was no significant difference between night and day, in or out of a solar eclipse. He did determine that the radiation detected at the highest altitudes he could reach was about twice that at sea level. The clear implication was that the radiation is coming from outer space. Robert Millikan, who later did research on the phenomenon, coined the term cosmic rays to describe it. In 1936, Victor Hess was awarded the Nobel Prize in Physics for the discovery of cosmic rays. In the decades that followed, evidence accumulated that cosmic rays are deflected by Earth's magnetic field, so they must be charged particles and not high-energy photons, such as X-rays or gamma rays, which have no charge. So in the sense of X-rays and gamma rays, which are high-energy forms of electromagnetic radiation, cosmic rays are not rays, they are particles, like alpha rays, helium nuclei, and beta rays, electrons. But the name stuck and they are still called cosmic rays. During the years from 1930 to 1945, a wide variety of investigations confirmed that the primary cosmic rays are positively charged moving near the speed of light. They are mostly protons with a mixture of approximately 10% helium nuclei and 1% heavier nuclei of elements such as carbon and iron. This composition is very similar to the abundances of elements found in the Sun and in interstellar space. Spaceship Earth makes a journey of 500 million miles around the Sun each year. Throughout this journey, a thin rain of cosmic rays produces a background of ionizing radiation on Earth. During the Apollo flights, astronauts reported seeing odd flashes of light, visible even with their eyes closed. We have since learned that the cause was cosmic rays. Cosmic rays are a definite hazard for astronauts, as they are for passengers and crew on high-altitude airplane flights, especially during solar flares, when the radiation doses from cosmic rays can reach dangerous levels. Even on Earth, our bodies are continually bombarded by cosmic rays, which damage or disrupt our molecules and are thereby potentially harmful to our health. Another bit of bad news is that cosmic rays can and do cause glitches in the operation of our computers. On the positive side, all this cosmic disruption can be put to good use to help answer questions and solve problems. As cosmic rays tear through Earth's upper atmosphere, they initiate nuclear reactions that change the nuclei of certain atoms. Some of these mutated nuclei, in the form of carbon-14 nuclei, so called because the nucleus contains 6 protons and 8 neutrons for a total of 14 nucleons, can be identified and used as clocks to date the charred embers of ancient campfires as well as bones and cloth. Recently, with the development of powerful new mass spectrometers, particle accelerators that whirl nuclei around at dizzying speeds and use their orbits to determine their masses, scientists are using nuclei produced by cosmic rays, called cosmogenic nuclides, to study the history of Earth itself. The principle is similar to that used for carbon-14. Cosmic rays produce cosmogenic nuclides of beryllium-10 and aluminum-26 in quartz crystals of rock and sand while they are exposed to the cosmic weather. The longer a quartz crystal is exposed, the more cosmogenic nuclides it accumulates. Isotopes formed by collisions with cosmic rays and exposed rock and sand crystals are washed down into streams where geologists can collect the sediment. This technique has been used by Darrell Granger of Purdue University to show that the ice sheet that formed Mammoth Cave in Kentucky arrived about 1.5 million years ago, about 700,000 years earlier than previously thought. At the other end of the scale, a group led by Friedhelm von Blankenberg in Switzerland found that the onset of cultivation in the rainforest of Sri Lanka increased erosion as much as 100-fold. Over the long haul, one might think that mountains wear down at a fairly steady rate. Not so, discovered Jim Kirchner of the University of California, Berkeley. His study of Idaho's mountains revealed that erosion rates over the past 5,000 to 27,000 years were 17 times higher than modern-day rates. Kirchner concluded that rare catastrophic events, such as wildfires followed by floods, were responsible for most of the erosion. This information is useful for engineers in estimating the time it will take reservoirs to fill with debris. That cosmic ray dating techniques should demonstrate the importance of catastrophes in shaping Earth is fitting in a way, because most of the cosmic rays that rain down on Earth are probably due to cosmic catastrophes, supernovas. Supernovas produce brilliant flashes of light and awesome shock waves that rip through interstellar space at speeds of millions of miles per hour. Part of the energy of a supernova shock wave goes into the production of hot gas that can be observed with an X-ray telescope. Another portion goes into the acceleration of electrons, whose radiation is observed with radio, optical, and X-ray telescopes. Not long after it had been demonstrated that cosmic rays are charged particles, Walter Baade and Fritz Zwicky suggested that supernovas were the source of cosmic rays. Later, in a classic 1964 monograph on cosmic rays, Russian physicists Vitaly Ginzburg and Sergei Siravatsky put this suggestion on much stronger footing. However, until recently, there was no direct evidence as to how protons and heavier nuclei are accelerated to speeds approaching the speed of light. Because cosmic rays are composed of charged particles, like protons and electrons, their direction of motion changes when they encounter magnetic fields throughout the galaxy. The origin of individual cosmic rays detected on Earth, therefore, cannot be determined. Chandra has helped to illuminate how supernovas produce cosmic rays. X-ray images of the Tycho supernova remnant show that the shock waves produced by the supernova behave in an unexpected way. The supernova debris is observed to expand at a speed of about 6 million miles per hour. This rapid expansion has created two X-ray emitting shock waves, the forward shock wave moving outward into the interstellar gas, and the reverse shock wave moving inward into the stellar debris. These shock waves, analogous to the sonic boom produced by supersonic motion of an airplane, produce sudden large changes in pressure and temperature behind the wave. According to the standard theory, before the Chandra observations, the forward shock wave should be about 2 light-years ahead of the stellar debris, half the distance from our Sun to the nearest star. What Chandra found instead is that the stellar debris has kept pace with the forward shock and is only about half a light-year behind. Similar effects have been observed for other young supernova remnants. The most likely explanation is that a large fraction of the energy of the forward shock wave is going into the acceleration of cosmic rays. Previous observations with radio and X-ray telescopes had established that the shock wave in Tycho's remnant was accelerating electrons to high energies. However, since high-speed atomic nuclei produce very weak radio and X-ray emission, it was not known whether the shock wave was accelerating atomic nuclei as well. The Chandra observations provide the strongest evidence yet that nuclei are indeed accelerated, and that the energy contained in high-speed nuclei is about 100 times that in the electrons. The detection of gamma rays from the Tycho supernova remnant supports this conclusion. The intensity of the gamma rays indicates that they are likely due to collisions between high-energy protons with interstellar atoms. These results, and similar ones from other supernova remnants, provide strong support for the idea that supernovas are the major source of cosmic rays that impact Earth. Extremely high-energy cosmic rays likely come from quasars produced by matter swirling into supermassive black holes, or possibly from shock waves created by intergalactic matter falling into clusters of galaxies. Based on the successes from the observations of the Tycho supernova remnant, scientists took an even longer look at it with Chandra. The new image of Tycho's supernova remnant revealed a peculiar pattern of stripes near the outer edge of the remnant. Assuming that the spacing between the X-ray stripes corresponds to the radius of the spiraling motion of the highest energy protons in the supernova remnant, the spacing corresponds to energies more than 30 times higher than reached in the Large Hadron Collider. The discovery of the X-ray stripes provides support for a general theory according to which magnetic fields can be dramatically amplified and tangled in supernova shock waves. The X-ray stripes are thought to be regions where the magnetic fields are more tangled than surrounding areas. Electrons become trapped in these regions and emit X-rays as they spiral around the magnetic field lines. However, the theory did not predict the regular and almost periodic pattern of the X-ray stripes, and clearly this is an important clue for further theoretical study. In the meantime, what Chandra has clearly established is that supernovas in our galaxy produce many of the cosmic rays that affect our lives and inform us about life on Earth. The cosmic environment that we inhabit profoundly affects us. Maybe not in the way the daily astrology columns portend, but in real practical ways. Some of these effects may be the source of earthly problems, and some of them can be used in the search for solutions to problems. The study of the intricate dances and pairings of low-energy electrons to form molecules of the various compounds that make up the world we live in may seem far removed from the thermonuclear heat in the interiors of stars and the awesome power of supernovas. Yet there is a fundamental connection between them. An atom of ordinary or baryonic matter, as it is called to distinguish it from the still mysterious dark matter, is composed of a cloud of negatively charged electrons orbiting a nucleus composed of protons and neutrons. Protons have a positive charge, and neutrons, as the name suggests, are electrically neutral. Although the nucleus of an atom has a diameter of only 1/100,000th that of the atom's electron cloud, the nucleus contains more than 99.9% of the mass of an atom. The number of protons in the nucleus defines chemical elements. All hydrogen atoms all have one proton in the nucleus, all helium nuclei have 2 protons, all carbon nuclei have 6 protons, and so on. Elements can have different isotopes, that is, the number of neutrons in the nucleus can differ. For example, a carbon-12 nucleus has 6 protons and 6 neutrons, whereas a carbon-14 nucleus has 6 protons and 8 neutrons. The formation of the elements began about 14 billion years ago, in the early minutes of the Big Bang. About 1 minute after the Big Bang, almost all the baryons in the universe were in the form of protons, the nuclei of the simplest element, hydrogen, with a mixture of neutrons. By the time the universe was 20 minutes old, the baryonic matter was a weighted mixture of 75% hydrogen nuclei, 25% helium nuclei composed mostly of 2 protons and 2 neutrons, and free-ranging electrons. A few 100,000 years later, the negatively charged electrons and positively charged nuclei would form neutral atoms. In essence, the history of the formation of the elements can be divided into two main phases, one that ended after the first 20 minutes, and another that has been ongoing since the formation of the first stars 13+ billion years ago. After that initial 1/3 of an hour, the expanding universe cooled below the point where nuclear fusion could operate. No further evolution of matter could occur again until hot, dense places were created again. This did not happen until a few million years later when the first stars formed. Then the buildup of elements heavier than helium could begin deep in the interiors of stars. There, the gravitational crush of overlying material compressed the gas and raised temperatures to millions of degrees. Nuclear fusion reactions turned on, fusing helium nuclei into carbon, carbon into oxygen, and so on. Winds of gas escaping from stars distribute some of this processed matter into space in a relatively gentle manner, and supernovas do it violently. This process was first described in detail in a monumental 104-page paper published in 1957 by E. Margaret Burbidge, Jeffrey R. Burbidge, Fred Hoyle, and William Fowler. Synthesis of the elements in stars described how stars synthesize nearly all the chemical elements heavier than hydrogen and helium, all the way up to uranium. This work is generally agreed to be one of the most important papers ever in astrophysics. It laid the foundation for a new kind of synthesis of astronomical observations with nuclear and particle physics, and paved the way for much of modern astrophysics. In the introduction to the paper, which became known as B²FH after the initials of their last names, the authors state that their goal is to determine the history of matter. This history is hidden in the abundance distribution of the elements, that is, the relative proportion of each element in the universe. A pie chart of the abundances of the elements shows that the simplest elements, hydrogen and helium, are far and away the most abundant, with oxygen and carbon coming in a distant third and fourth. This preponderance of hydrogen and helium is strong evidence that the elements in the universe have been created by a process in which the heavier elements are built up from the lighter ones, starting with hydrogen. This process is called nucleosynthesis. As stars evolve, depending on their mass, they go through a sequence of stages in which nuclear fusion reactions build up heavier elements and, in the process, supply energy to support the star against the crushing force of gravity. Ultimately, processed matter containing heavy elements, any element heavier than helium is considered a heavy element by astrophysicists, is expelled into the interstellar medium either by stellar winds or by supernova explosions. One of the principal scientific accomplishments of Chandra has been to help unravel exactly how the enrichment by stellar winds and supernovas works on a galactic and intergalactic scale. Chandra images and spectra of individual supernova remnants make it possible to track the speed at which clouds of gas rich in elements such as oxygen, silicon, sulfur, calcium, and iron were ejected in the explosions. In some cases, it is possible to construct three-dimensional images, which will be key to developing accurate models for the explosion process. On a galactic scale, observations indicate that stars are forming extremely rapidly in certain peculiar galaxies called starburst galaxies. Starbursts are apparently triggered by collisions with other galaxies. These collisions initiate the collapse of interstellar clouds. In the Antennae galaxy system, a collision of two galaxies has created several bursts of star formation. When galaxies collide, the stars in the galaxies do not. Their target area is too small, but large diffuse clouds of gas do, and they did collide frequently in past events. These collisions sent shockwaves rumbling through the clouds. Tens to hundreds of millions of stars formed in a few million years, a lost weekend or so in the life of a galaxy. Millions of years later, this baby boom leads to a death boom in the form of many supernovas. These heat the interstellar gas and enrich it with heavy elements. Another unexpected agent for distributing heavy elements throughout a galaxy is a supermassive black hole in the center of the galaxy. Violent winds and jets produced by rapidly spinning black holes can drive material enriched with heavy elements into the outer reaches of the galaxy and beyond. Gas can also be stripped from a galaxy if the galaxy falls into a galaxy cluster. The motion of the galaxy through the hot intergalactic gas produces a ram pressure that acts like a wind, in much the same way that a motorcyclist traveling at a high speed feels a strong headwind. This so-called ram pressure wind blows the cool gas out of the galaxy into the intergalactic medium and enriches it with the heavy elements produced by stars in the infalling galaxy. On a still larger scale, evidence for oxygen has been detected in intergalactic filaments of gas millions of light years in length. This oxygen was likely produced more than 10 billion years ago, in some of the first supernovas to occur in the evolution of the universe. In some starburst galaxies, the rate of supernovas gets so high that the combined effects of many supernova shock waves drives a galactic-scale wind that blows the gas out of the galaxy. A prime example is the galaxy M82. Galactic winds such as the one in M82 are rare today, but they were probably common billions of years ago when galaxies were very young. Running the expansion of the universe backward to that time implies that galaxies were closer together then. Collisions between galaxies were much more common than in the present epoch. These collisions produced more starbursts and millions of years later more supernovas, which overheated the interstellar gas to the point that it expanded out of the galaxy into intergalactic space. A Chandra report on the detection of oxygen ions in the Sculptor Wall, a vast collection of gas and galaxies that stretches across millions of light years, may be evidence that this process occurs on a vast scale. As the enrichment of the interstellar and intergalactic gas and heavy elements has proceeded over vast stretches of space and eons of time, the chemistry of the cosmos has become more complex. Subsequent generations of stars have formed from interstellar gas with more heavy elements. Our Sun, solar system, and indeed the existence of life on Earth are direct results of this long chain of stellar birth, death, and rebirth. In this way, the evolution of matter, stars, and galaxies are all inextricably tied together, and so too are astronomy and chemistry. The message is both simple and profound. As time passes, things change. The elements which are the bedrock of our existence change into other elements. Impermanence rules. Stars are born, exist for a while, sometimes for a very long while, but then they explode, implode, or just slowly cool into obscurity. Of course, on the human scale, we knew this already. It is the ecstasy and agony of our existence. We are born, we live, we love, friends and loved ones die, and so do we. And yet, a few years ago, I attended a memorial service for Geoffrey Burbidge, who was my PhD thesis advisor a long time ago. A colleague whom I had not seen for years remarked, "People don't really change that much, do they? They grow old, but the fundamentals are still there. You can tell they're still the same person." Jeff certainly didn't change. To the end, he steadfastly stuck to contrarian points of view on the Big Bang and related topics, which pushed him out of the mainstream of physics, where he had once been such a commanding figure. On a more personal level, he remained a gruff, intimidating presence. I became his graduate student because the other students avoided him, and I, being green, fresh from Oklahoma and clueless, didn't know any better. As it turned out, it was a stroke of luck for me. He became a mentor who guided me into X-ray astronomy and helped me get my first job in astrophysics. Then he became a friend who, when I was in the depths of despair and helpless to prevent a catastrophic change, was one of the first to call me and offer his friendship, support, and consolation, even though he himself was ill. Simple acts of kindness and consideration. They may not seem like much, but they can offer something of unchanging value as we struggle to cope with a changing universe. Except for the studies of the cosmic microwave background radiation, virtually all research in cosmology and extragalactic astrophysics depends on knowledge of how stars form and evolve. Yet, despite considerable progress in characterizing and understanding star formation in isolation and in small molecular clouds, knowledge of star formation is limited, with fundamental questions still unanswered. What is the relative proportion of low, medium, and high-mass stars that form when a huge cloud of dust and gas collapses and fragments into stars? What exactly triggers the formation of stars? How many stars have disks that will be the birthplace of planets? One of the first steps toward answering these questions is to observe interstellar clouds at various stages in the star formation process. To use an old but good analogy, astronomers have learned to piece together the essence of the billion-year drama of stellar evolution. They have done this in much the same way that an observant biologist could understand the general outlines of the life cycle of trees in the forest by spending a day in the forest, even though the trees may live more than 100 years. The biologist could take note of the location and numbers of acorns or pine cones, sprouts, and trees at various stages of growth. In the same way, astrophysicists can observe stars of different ages and masses and reconstruct the life cycles of stars. Extensive catalogs of stars have been compiled, listing properties of the stars such as luminosity, color, and so on. And these data have been used to develop the theory of stellar evolution. It turns out that there are many more low-mass stars than massive ones. At the very lowest end of the mass scale are brown dwarfs, which have a mass of only a few % of that of the Sun. Brown dwarfs cannot sustain nuclear reactions, so they never evolve, and they spend their lives in a limbo state between that of a planet and a star. The faintness of brown dwarfs makes them difficult to detect and to assess just how abundant they are in the galaxy. The formation of a star begins with the collapse of a cloud of dust and gas. In the early stages, the energy released by gravitational collapse heats the interior of the star. This is the so-called protostar stage of star formation. After a few million years, the material in the center of the protostar becomes so dense and hot that the nuclear fusion of hydrogen nuclei into helium nuclei can occur. The outflow of energy released by these reactions provides the pressure necessary to halt the collapse. A star is born. Stars progress through their lives as balls of gas heated by thermonuclear reactions in their cores. If they have masses less than a few suns, they will end their lives as white dwarf stars. The more massive stars explode as supernovas, leaving behind neutron stars or, in the case of the most massive stars, black holes. Indeed, the development of an understanding of how stars evolve is one of the great triumphs of 20th century astrophysics, if not all science. Many details remain to be worked out, especially on the front end, when stars form. In what follows, I lump protostars and young stars together as young stars, since it is difficult to assess the precise boundary between the two stages. What is known is that stars do not form in isolation, but in clusters, which can have thousands of members. Because the stars in a cluster were all born at roughly the same time and are at roughly the same distance from Earth, a star cluster provides an ideal laboratory for testing theories of how the behavior of a star relates to its mass. Most star clusters eventually disperse, so we see them when the stars are relatively young, with ages less than a few 100 million years. One problem is that much of the star formation process takes place in the dark, inside dense clouds of gas and dust. The dust in particular absorbs optical light so efficiently that even the most powerful optical telescopes cannot see what is happening there. As a look at almost any of the beautiful images taken with optical telescopes shows, there are also a lot of stars in the field of view, most of which have nothing to do with the star-forming cloud. They constitute an attractive nuisance as far as understanding star formation is concerned. Fortunately, help has arrived in the form of Chandra, with its ability to make sensitive, high-resolution X-ray images of star clusters and their environs. X-rays are largely unaffected by dust, and it helps that young stars are fairly strong X-ray emitters. The galactic field stars in the foreground are mostly older, weak X-ray emitters, so they are a minor problem. Chandra's spatial resolution makes it possible to distinguish individual stars, something other X-ray astronomy missions could not do. Previously unseen populations of stars, embedded in gas and dust and invisible to optical telescopes, have been discovered. At a distance of about 1,400 light-years, the Orion Nebula Cluster is the closest large star-forming region to Earth. Chandra images show about 1,000 X-ray emitting young stars in the Orion Nebula star cluster. The X-rays are produced in the hot, multi-million-degree upper atmospheres, or coronas, of these stars. Multiple Chandra observations of the Great Nebula in Carina, a star-forming region in the southern hemisphere, have yielded a catalog of more than 14,000 X-ray point sources. More than 12,000 of these are young stars with ages between 1 million and 10 million years. One significant advance made possible by these observations is the development of a method to estimate stellar ages in young star clusters based on a combination of X-ray and infrared observations and theoretical models for the evolution of protostars and young stars. This method has been applied by a team of scientists from Penn State University to derive median ages for thousands of stars in 17 massive star-forming regions. They found that star-forming regions are not uniformly populated with young stars of the same age. Rather, the stars form in clumps or subclusters. Large differences in stellar ages across the clusters indicate that star formation occurs in waves. Detailed Chandra and infrared studies of the Flame Nebula, NGC 2024, and Orion Nebula Cluster show that the progression of star formation in a large interstellar cloud can be traced over spatial scales of several light-years and timescales of several million years. In the Flame Nebula, the stars in the center have ages of about 200,000 years, whereas those on the outskirts are about 1.5 million years old. The data imply that some star clusters form slowly, that the apparent age ranges are real, and that star clusters do not necessarily form from the inside out. For example, if a supernova happens to occur near the edge of a cloud, it can drive a shock wave, which triggers a wave of star formation. Sometimes the radiation from an extremely luminous star before it goes supernova is sufficient to drive a shock wave and initiate star formation in the vicinity. A major finding of recent research, primarily with infrared telescopes, is that very young stars are usually surrounded by accretion disks of dust and gas. As with disks around black holes, these disks are a natural consequence of the collapse, with random gas motions averaging out to go with the flow of angular momentum, producing a flat disk like a pizza. Some of this matter will fall from the disk onto the young star. The accretion of gas may produce X-rays as the particles collide with the atmosphere of the star. As with accretion into black holes, the combination of rotation and magnetic fields may produce a jet of gas streaming away perpendicular to the accretion disk. Circumstellar disks are the raw material from which planets will form, so they are of great interest in efforts to understand how planets are formed. An important question is the survival of circumstellar disks in the often harsh conditions of a star-forming cloud. A deep Chandra observation, combined with optical and infrared studies of the approximately 3-million-year-old Trumpler-16 star cluster in the Carina Nebula, investigated this question. It revealed that a large fraction of the circumstellar disks around low-mass stars have survived the intense radiation field of the cluster's massive, luminous stars. However, the disks around the massive stars do not fare so well, and the survival rate of these disks is several times lower than that of the low-mass stars. Chandra and infrared surveys found that the disk fraction for stars with masses greater than twice that of the Sun is about 20%, whereas the fraction for stars with masses comparable to that of the Sun is about 50%. Disks around massive stars evidently have a shorter dissipation timescale than those around lower-mass stars. Even for low-mass stars, radiation and the disruptive influence of the gravity of the young star take their toll. Comparative studies of many star clusters suggest that the fraction of stars with disks is about 80 to 90% in young clusters less than about 1 million years old. By 5 million years, the disk fraction drops to 20%, and after 10 million years, almost all disks have dissipated, having been blown away or accreted onto their parent star. This means that the formation of gas planets has to be completed within about 10 million years before all the material that will form the planets is gone. Now that the time scale for the destruction of circumstellar disks has been fairly well established, it is possible to flip the relationship and use the percentage of disks around stars as a method for estimating the age of a young star. A young star is much more likely than an old one to have a disk. Chandra, optical, and infrared observations of the massive young cluster NGC 6611 and its parental cloud, the Eagle Nebula, indicate that waves of star formation have swept across this nebula. A giant shell of cool molecular hydrogen gas, about 600 light-years wide, likely was created by a wave of supernova activity 6 million years ago, followed by another wave 2 to 3 million years ago, and a third wave 300,000 years ago. Strong X-ray emission from young stars indicates that a significant amount of matter is accreting from the circumstellar disk onto the star. This accretion, which is stronger for young stars less than a few million years old, is likely guided by a magnetic field connecting the disk and star. The magnetic field can become twisted and tangled in this process. In addition to producing jets, it can cause intense flaring on the star. A long Chandra observation of the Orion Nebula star-forming region has shown that virtually all young stars exhibit powerful flares up to 10,000 times stronger than the flares on the present-day Sun. A strong feedback loop could be at work around these stars. Intense flares, occurring typically once a week, can heat the circumstellar disk and ionize it, creating more turbulence in the disk, which creates more accretion, which produces more flaring. It is not known what the ultimate effect will be for the formation of planets. On the one hand, the process could consume most of the gas before planets could form. On the other hand, the increased turbulence could encourage planets to form. The X-ray study of exoplanets is rapidly developing in an effort to answer these and other questions. In the case of giant planets in the solar system, located several 100 million kilometers from the Sun, residual heat from formation plays an important role in their energy budgets, and direct radiation from the Sun is less important. The so-called hot Jupiter exoplanets, by comparison, are 10 to 30 times closer to their parent stars and receive 100 to 1,000 times more radiation from their stars. Stellar X-rays, especially during flares, can cause excess heating and atmospheric changes, and over the lifetime of the planet could erode away as much as 25% of its mass. The star-planet interaction works both ways. For several stars with exoplanets, there is an indication that a significant increase in X-ray activity coincides with the closest approach of an exoplanet to the parent star. The effect of X-rays from the parent star on its planets is not confined to the turbulent youth of a star. Chandra's observations of the transit of the hot Jupiter exoplanet HD 189733b around a 5-billion-year-old star similar to the Sun show that, when this exoplanet eclipsed its parent star, it produced a significantly deeper dip in soft X-rays than at optical wavelengths. This difference is attributed to a thin outer planetary atmosphere. The observations suggest that this atmosphere has a radius 1.75 times the planetary radius and is transparent at optical wavelengths but opaque to X-rays. The parent star has an anomalously high X-ray luminosity for its age, as does another planet-hosting star, CoRoT 2a.51. This observation could be evidence that the hot Jupiters in these systems, in effect, are keeping their parent stars young and active by transferring angular momentum from the planetary orbit into the stellar spin. With the dizzying pace of discovery of exoplanets, it seems certain that observations of stellar exoplanet interactions will be one of the most exciting areas of research for Chandra in the years to come. Pulling back for a larger view, the Chandra image of the Tarantula Nebula in the Large Magellanic Cloud, a nearby galaxy 160,000 light-years away, provides a tableau of the drama of star formation and evolution. The Tarantula, also known as 30 Doradus, is in one of the most active star-forming regions in our local group of galaxies. Massive stars are producing intense radiation and searing winds of multi-million-degree gas that carve out gigantic superbubbles in the surrounding gas. Other massive stars have raced through their evolution. They have been exploding catastrophically as supernovas and leaving behind neutron stars and black holes. The expanding supernova remnants chemically enrich the interstellar medium of the galaxy, drive turbulence, generate cosmic rays, and trigger the collapse of giant clouds of dust and gas to form new clusters of stars. In other words, they are agents of renewal. I witnessed an earthly sample of a similar process a few years ago in a rural area of Southern California. Extremely dry Santa Ana winds had whipped the smoldering ashes of a controlled burn back to life. In a matter of hours, a full-fledged wildfire was racing through a river valley and up steep canyon slopes at speeds reaching 25 miles per hour. Within 24 hours, 45 homes were burned to the ground, and 5,000 acres of chaparral, sagebrush, and avocado groves were blackened. Thankfully, no one was killed, although some residents managed to survive only by immersing themselves in a cold swimming pool. Looking at the thick layer of ashes and the charred stumps of manzanita and live oak, it was difficult to imagine how the area would ever recover. Yet, the following winter a series of light rains fell, and by springtime the hills were alive with all the colors of the rainbow in one of the most dazzling wildflower displays in my memory. The rug of gray ash had been transformed into a magic carpet of blue Canterbury bells and golden California poppies, and black limbs were sprouting green. The process of renewal had begun, and in extravagant fashion. Renewal is a constant theme of nature, often triggered by violent events that unlock potential that has remained dormant for years, as in the wildflower seeds. Fortunately for us, many of the most dramatic examples of renewal occur not in our backyard, but thousands of light-years away, where they can be safely observed with telescopes such as Chandra. Now, well into its 18th year of operation, Chandra has given us an unparalleled look into a realm of high-energy phenomena and fundamental physics not readily accessible with other telescopes or with laboratories on Earth. And we have learned many cool things about the hot universe. These discoveries, while advancing our knowledge, have often revealed an underlying richness and complexity waiting to be explored. Chandra is in excellent condition, And so, on the premise of what's past is prologue, we can expect that it will continue to play a major role in this exploration.